It's my great pleasure to introduce the first speaker of our conference, Professor Efim Zelmanov from Southern University of Science and Technology, and he will tell us about growth functions of algebras.
Thank you. Can I share the screen?
Sure.
Okay. Okay, I will talk about growth of algebras. But not only of algebras, also growth of groups, monoids, all things that grow to become infinite from a finite set of generators. Now I'm trying to understand how to deal with. Okay. As Mikhail Gromov and Leo Tolstoy said, all finite groups grow in the same way. Each infinite group grows in its own way. So let G be a finitely generated group. So an arbitrary element can be represented as a product of generators and their inverses. We consider products of lengths up to n. If you look at the Kelly graph, which is a metric space, then it is just the ball of radius n with the center as the identity element. These balls grow, their union is the whole group, and the number of elements in the ball of radius n, so the number of products of lengths up to n, is a value of the growth function. Unfortunately, this growth function depends on the system of generators. Therefore, we need to introduce some equivalence between functions. Given two functions of natural argument, two increasing functions, we say that f, the function f, is asymptotically less or equal than the function g if there exists a constant c such that for an arbitrary n, we have this inequality. If the function f is less or equal than g, and the function g is less or equal than f, then these functions are asymptotically equivalent. Now, if you choose two finite generating subsets of g, then the corresponding growth functions are asymptotically equivalent. So a growth of a group is a class of equivalence it's not a function. Motivation. The motivation for this study came from geometry. Schwarz, Yefimovich, Milner noticed that if you consider a Riemannian manifold and fix a point, then the growth of volumes of balls with the center at that point is asymptotically equivalent to the growth that I have described of the fundamental group. And another reason is this is the way to compare infinite groups. If you have two finite groups, you can say that, well, one of them has bigger order than the other one. But if you have two countable groups, what can you say? You can discuss which group grows faster. The same can be said about monoids. We count all products of length n, but no inverses. And it can be said about hereditary languages. I will say a few words about hereditary languages. Fix a finite alphabet and fix a family of bad, prohibited words. Now we consider all words that do not contain bad words as subwords. And we add 0 artificially. So we get the language, what is called language. Stepin and Grigorchuk found some very interesting explicit formulas for growth of this language. So the number of words of given lengths. Now let's talk about algebras. Let F be a field and we consider a finitely generated algebra. So an algebra generated by a finite dimensional vector space V. So far, let us consider only associative algebras. Vn is the span of all products of lengths up to n of elements from V. This is a finite dimensional vector space. This finite dimensional vector spaces grow, and their union is the whole algebra. Now the growth function is the dimension of this vector space. In 65, Gelfand and Kirillov defined the so-called Gelfand-Kirillov dimension of the algebra A. If the growth function is polynomially bounded, then the minimal degree of all of these functions that bound the growth functions is called Gelfand-Kirillov dimension. They just needed to show that two infinite dimensional algebras are not isomorphic. How do you do it? So they introduced this invariant and computed it. In 68, John Milner published a very influential survey in Mathematics Monthly, that is a magazine for undergraduate students. In this survey, he formulated two problems. Problem one, is it true that a group has polynomially bounded growth if and only if it has a subgroup, an nilpotent subgroup of finite index? So virtually, if G is virtually nilpotent. And problem two, do there exist groups with intermediate growth? And in early 80s, both problems were solved. Mikhail Gromov solved the first problem. Indeed, all polynomially bounded groups with polynomially bounded growth are virtually nilpotent. And in 83, Rostislav Grigorchuk constructed an example of a group of intermediate growth. Intermediate means that this growth function grows faster than any polynomial and slower than any exponential. Now, what is the growth? What is the actual growth of the Grigorchuk group? Let's consider this cubic equation. This cubic equation has a root, alpha, which is approximately equal to this number. Let us consider the logarithm of 2 with this base alpha. It is approximately equal to this. Bartholdi, Erschler, and Zheng proved that the growth of the Grigorchuk group is asymptotically equivalent to this function, which is, of course, intermediate. Bartholdi proved that this is the upper bound, and Erschler and Zheng, relatively recently, proved that it is also a lower bound. And if you look at the proof, you won't think that this is a paper in algebra. It's random walks, probability, and so on. Okay, the basic question for groups, algebras, monoid, for all infinite objects that grow from a finite subset is which functions appear as growth functions up to asymptotic equivalence. Of course, not all functions. If g of n is a growth function, then of course it is an increasing function, and it is submultiplicative, because every word of length m plus n can be divided into a word of length m and a word of length n, and so you have this inequality. And for many years, there was an open problem. Is it true that increasing submultiplicative functions is exactly the class of functions that are asymptotically equivalent to growth functions? What is known? Let's talk again about growth functions of groups. Bartholdi and Erschler proved this that if an increasing function lies in this interval, B, you remember I talked about the cubic equation, B is that B. And also this function is sufficiently regular. It means that I don't want to list all the conditions. Then this function is asymptotically equivalent to growth function of a group. There is an open conjecture, which is due to Grigorchuk, that there is a gap. There are no groups with growth line between polynomials and this function. Grigorchuk proved it for residually P groups. Using Lazar's theorem of p-adic analytic groups. Okay, now let us talk about Gelfand-Kirillov dimension. All finite dimensional algebras have Gelfand-Kirillov dimension 0. Of course, there is nothing between 0 and 1. There is an algebra, polynomials in one variable has Gelfand-Kirillov dimension 1, and then nothing between 1 and 2. It was first proved by Hedlund and Morse in 1938 in different language, then reproved by Bergman. So now it is known as Bergman gap. Starting with 2, every number is a Gelfand-Kirillov dimension of some algebra. This series of examples was constructed by Bohr and Kraft. Bartholdi and Agathos Maktunovich proved that if gamma is an increasing submultiplicative function, then there is a growth function which is kind of close to gamma. That was a move in the direction of the proof of the conjecture that I formulated. There are more algebras of intermediate growth than groups of intermediate growth. Why? What do I mean? Martha Smith proved in 1976 that if a Lie algebra is of subexponential growth, then its universal enveloping algebra also has subexponential growth. So if G is a finite dimensional Lie algebra, and we consider polynomials in one variable over G, then the growth of this Lie algebra is linear. And the universal enveloping algebra has intermediate growth. It's not polynomial, because by Poincaré-Berger-Witt theorem, only finite dimensional algebras have polynomial growth of the universal enveloping algebra, and it is subexponential by Martha Smith theorem. Now, I will talk about the description of all growth functions of algebras, monoids, and hereditary languages. You know, by every hereditary language is essentially a monoid. Every group is also a monoid. So you would expect that there are more growth functions of monoids than growth functions of hereditary languages. And for every monoid, you can consider semi-group algebra. But in fact, it is the same classes of function for algebras, monoids, and languages. Let capital F of n be an increasing function, and we consider its discrete derivative. The following theorem appeared in our joint paper with Jason Bell. Suppose that the derivative is greater or equal than n plus 1, submultiplicativity for derivatives, and this inequality, it does not follow from submultiplicativity, because I never said that the derivative f is an increasing function. Now, if all three conditions hold, then f of n is asymptotically equivalent to a growth function of a hereditary language, hence of a monoid, hence of an algebra. And any non-linear growth function, well, linear functions, of course, everything is clear with them. Every non-linear growth function of an algebra satisfies all three conditions. So this is a description. And so in this description, the conditions are imposed not on the function, but on the derivative. immediately after this theorem, Beery-Greenfeld found an increasing submultiplicative function such that the derivative is not asymptotically equivalent to a submultiplicative function. Because if the derivative has submultiplicative, you can integrate it, and then the function is also submultiplicative. But in the other direction, it doesn't work. So it was a kind of exercise in calculus. And therefore, the original conjecture is not true. The conditions should be imposed on the derivative. Remarks. These conditions, 1, 2, 3, are not asymptotically invariant. We know asymptotically invariant versions of these conditions, but they are much more technical. And unfortunately, when we take a function and construct an example, we construct a language with this function as a growth. And this language contains many words that are not extendable to an infinite words. In a way, it is junk. It would be interesting to understand the growth if you count only extendable words, essential words. But that, for example, would imply that the second derivative of the growth function is non-negative. Okay, all subsequent unassigned results are my joint results with Beery-Greenfeld. So if I don't indicate the authors, it is with Beery-Greenfeld. Growth of modules. Let A be a finitely generated algebra. Well, so it is generated by a finite dimensional subspace V. Let M be a finitely generated module. It is also generated by a finite dimensional subspace W. Then the growth function is this function, the function dimension of this finite dimensional subspaces. Theorem 2, every increasing function, which is asymptotically less or equal than the exponential, can be realized as the growth function of some module. And since we understood the growth function of modules, we were able to answer one of the questions in the Krause-Lennegan book. This is the kind of the basic book on Gelfand-Kirillov dimension, and it contains a number of questions. So they asked what happens if a module is an extension of two finitely generated modules and both have finite Gelfand-Kirillov dimension. So we constructed an extension which has infinite Gelfand-Kirillov dimension, which answers the question. Well, now let us talk about nil algebras. An associative algebra A is called nil if an arbitrary element is nilpotent with some power. Some power of that element is equal to 0. This is a very interesting class. In 1941, Alexander Kurash formulated one of the most influential problems in the theory of associative algebras, the so-called Kurash problem, which was analog of the Burnside problem about torsion groups. He asked if a finitely generated associative nil algebra is finite dimensional and nilpotent. In 1964, Golod constructed counterexamples, and he used these current counterexamples to construct the first examples of finitely generated infinite torsion groups, which answered the question of Burnside. Latyshev and Small independently asked if Kurash problem has positive solution in the class of algebras of polynomially bounded growth, so algebras of finite Gelfand-Kirillov dimension. If you asked about the Burnside problem in the class of groups with polynomially bounded growth, the Burnside problem has positive solution. It follows from Gromov's theorem. However, for algebras in 2007, Tom Lenagan and Agatas Moktanovich constructed counterexamples, but only over countable fields. They constructed finitely generated nil algebras of finite Gelfand-Kirillov dimension. In the subsequent paper joined with Alex Young, they decreased this Gelfand-Kirillov dimension. It lies now between 2 and 3, but we don't know precisely what is it equal to. Probably again some root of a cubic equation or whatever. Speaking of uncountable fields, Bell and Young proved that for every super polynomial function, that is functions that grows faster than any polynomial, there exists a finitely generated nil algebra with this growth. Now, what are growth functions of nil algebras? My conjecture is that all functions of theorem 1, well, nonlinear, can be realized as growth functions of nil algebras. So there are as many growth functions in nil algebras as in all algebras. The following result is a step in this direction. Let P of n be the growth function of the Lenagan-Moktanovich-Young algebra. So it lies in this segment. Let f of n be an arbitrary increasing submultiplicative function. Then this function is asymptotically equivalent to a growth function of some finitely generated nil algebra. But that is only for countable fields. For uncountable fields, the result is less precise. Let delta of n be an arbitrary increasing function. Let omega of n be an arbitrary increasing superpolynomial function. And let f of n be an arbitrary increasing submultiplicative function. Then there always exists a finitely generated nil algebra with a growth function line satisfying these inequalities. So both left-hand side and right-hand side are close to the function f of n, but only close. Now let us talk about algebras of oscillating growth. That is growth that sometimes is close to one function and sometimes close to another function. In 2013, Martin Kasabov and Igor Pak constructed groups with growth functions oscillating between a given intermediate function, like something like this, and an arbitrarily rapid sub-exponential function. You know, it's a philosophical question. Why do we need to study growth functions? That is the way to study groups, because when you construct all these examples, you construct examples of groups of given growth. And I must say that all examples, I mentioned already quite a few, are somewhat close to Grigorchuk groups. Of course, it depends on from which distance you look, but they all act on some counter sets in a certain way. So in some sense, they're all close to Grigorchuk groups. It would be very interesting to find subgroups of sub-exponential growth based on really different ideas. In 2021, Viktor Petrogradsky construct analogs of Grigorchuk groups, constructed restrictedly algebras that are analogs of Grigorchuk groups. And then he constructed nil restrictedly algebras, of course, over fields of positive characteristic that oscillate between functions very close to linear functions and functions close to exponentials. Now we constructed associative nil algebras over fields of arbitrary characteristic with oscillating growth functions. And if you constructed associative nil algebras, then you can get in Lie restricted Lie algebras from them. So over arbitrary characteristic. Theorem, again, you should make a difference between countable fields and uncountable fields. Let f be a countable field, let f be a sub-exponential function, then there exists a finitely generated nil algebra such that this inequality holds infinitely often, epsilon is an arbitrary positive number, and this inequality holds infinitely often. So the function oscillates. Over arbitrary fields, let f of n be a sub-exponential function. Again, omega of n is an increasing super polynomial function. Then there exists a finitely generated nil algebra which infinitely often satisfies both inequalities. We can construct oscillating growth function even for domains. Domain is an algebra where product of two non-zero elements is non-zero. So let f of n be a sub-exponential function. There exists a finitely generated domain such that this inequality holds infinitely often, and this inequality also holds infinitely often. And this immediately has a corollary that answers another question from Krause and Lenagan. It's about tensor products. The growth function of a tensor product is less or equal than the product of growth functions. It's obvious. Therefore, the Gelfand-Kirillov dimension of the tensor product is less or equal than the sum of Gelfand-Kirillov dimensions. In 84, Warfield showed that the inequality could be strict. The left-hand side could be strictly less than the right-hand side. And he asked the question, to which extent the left-hand side could be smaller than the right-hand side. More precisely, if alpha is the Gelfand-Kirillov dimension of the algebra A, beta is Gelfand-Kirillov dimension of the algebra B, and they are nonlinear, then is it true that any value in this segment can be made Gelfand-Kirillov dimension of a tensor product? In 87, Krempa and Takninsky showed that yes, but their algebras had big radicals, and the proof mostly played with radicals, was a play with radicals. So they all asked the question, if you can find semi-prime examples. And from these examples with oscillating growth functions, we can construct semi-prime examples. Okay, I spoke for half an hour, not 40 minutes.
Thank
Thank
you.
you.